Okay, I think people are trickling in, and so hey.
Oh, suddenly this thing went.
No, you can share your presentation, Ramanand. You can put it up.
Yeah, but he himself went, I think.
Oh, right, I think his connection. Right.
Yes.
I think he'll come back.
Yeah, his connection went.
Mm.
He's coming from home, so.
Mm. So let's wait. I don't know whether we need to call him, but I'm sure he's trying.
Santosh, just keep a lookout.
Yes, sir.
Yeah, I don't think the waiting room is enabled. So
Yes. So. Oh, it was all perfect and suddenly it disappeared.
it's absolutely perfect. Do you know his number, Kandu?
No, I gave him my number so that if he
him.
wants, he can call me. But let me check.
So, sometimes this question comes that this is being live streamed or this will be this is being recorded. So if you press the wrong button, let's say instead of OK, you said no, then do you get disconnected?
That's possible. I don't know. I pressed some button and I was, there you are.
So it first said, recording. So I clicked OK, and the next time I just clicked the cross button, and then the screen.
Okay, correct.
Yes.
So Santosh, can you make his co-host? You can share again, Raman.
Yeah, I'll do that. Yeah. I mean, it took me a minute or so to realize that.
No, so Sanjit got it even before you did. Sanjit got exactly what happened.
Yes, absolutely.
Is my screen visible now?
Yes.
You make it full screen if you can. Yeah, thanks. Great, wonderful. So let's start. I mean, we are absolutely on time. Welcome again to our Thursday Colloquium group. We've been doing this for 1.5 years now, and actually, I am very happy to see that still people are coming together on Thursday. We've now moved to every other week, and sometimes we want to go away from our mainstream subjects that we normally deal with. And I'm very happy to invite Professor Ramanand Chakraborty from the Center for Earth Sciences at the University of Science, Bangalore, to talk about a related subject in geochemistry, geophysics, and evolution of planetary system. Ramanando did his undergraduate from Presidency College, Geology Department, IIT Kharagpur next, and then went to his PhD at the University of Rochester, and then worked very, very interesting, of course, interdisciplinary department at Harvard University called the Origins of Life, where a lot of the astronomers, geophysicists, biologists, chemists, all kinds of people come together. And he worked there for several years and then joined IISc in 2011. He received the Sean Jayanti Prize fellowship a few years ago, and I'm very happy to see what he has to say about planetary evolution. Over to you, Raman.
Well, thank you, Professor Rachadri, for the invitation, and also Professor Kandaswamy, and thanks for the introduction. It's a pleasure and honor to actually speak, in front of a very different audience. And as Professor Rachadri was mentioning, the last time I, did this kind of presentation when I was a postdoc, and I had to present my work in front of astronomers. So, but I'm a geologist and more specifically a geochemist by training. So before we get to the talk, maybe I'll spend a couple of minutes just telling you what is our scientific approach when we try to deal with problems, right? So, this is an isotope geochemist's toolbox, and what we do is we utilize radioactive isotopes, we utilize radiogenic isotopes, the traditional stable isotope systems of oxygen, carbon, nitrogen, sulfur, and hydrogen. And more recently, there's this field of non-traditional stable isotopes, which have actually cropped up. And so you basically use these isotopes as tracers of natural processes. And these processes could have happened 4.5 billion years ago, or could have happened, or basically are happening today. Let's say if we're analyzing rivers. So Earth science mostly deals with inverse problems. Unlike many other, I guess there's a lot of similarity with astronomy, because what you're observing today also happened several million years ago. But the same thing in Earth science. So we're mostly dealing with inverse problems. So when you have a sample and you measure its isotopic compositions, you need to correct for effects of radioactive decay, chemical effects, cosmic spallation, and eventually go back almost 4.5 billion years ago when our solar system essentially formed. And then there is a section of Earth scientists who are only interested in the first few million years of the solar system. And that is the period from the isolation of our solar nebula to formation of the first round solids in the solar system. And that is the period of the Holy Grail, because that's when we basically have our initial compositions, right? And this is important because, as we all know, our own sun, which is more than 99% of the mass of the solar system, is essentially burning hydrogen to form helium. But if you look at solar spectroscopic data, we know that the sun is actually made up of even slightly heavier elements. Of course, hydrogen and helium are the most abundant ones, but you have all the heavier elements. And if you look at anything around you, you're made up of carbon, you're made up of nitrogen, and oxygen and hydrogen. And as Carl Sagan famously pointed out, we are all made up of stardust, right? So all the heavy elements are actually, they're part of the interstellar media, whose composition has been changing over time because of all the other sources that are listed on the left. So what we start off with when the planets form is somewhat important. And so with that introduction, let me tell you what I'll be trying to present in today's lecture. I'll be talking about impact cratering and its importance in the early solar system and the other implications they have, and then focus on terrestrial impact craters and specifically go into the details of a geochemical study of this one crater which is in India called the Lunar crater, and then we will look at what happens during cratering and then what implications they have in terms of evolution of planetary bodies. The last part of the talk, I'll briefly talk about collision-related volatilization that is evident on, evident in meteorites, which means their parent bodies, and the samples of the moon which we have at our disposal. So with that, let's get started. And so impact craters are ubiquitous features in the solar system. You look at any planetary body in our solar system, you will see all these pock marks all over. You can look at the moon, you can look at Venus, Mars. This is 4 Vesta is one of the largest asteroids in our asteroid belt, and this is an example from Mimas, which is a moon of Saturn. And if you look at craters, they have a wide variety of sizes. On the left, you have a little pit which is 10 microns in size, and this is from lunar soils where where you find these craters because of micrometeorite impacts. And then you can have simple craters just a few kilometers in diameter. You might have larger craters which are known as complex craters, which have this rim and a central uplift, and then the gigantic ones, which might be a few hundred to a couple thousand kilometers in diameter, where you find this ripple-like structures, this ring-like structures, and it could be multiple rings and so on and so forth. So these craters are not only ubiquitous, they come in different sizes, they have different morphologies. And much of our knowledge of impact craters essentially comes from the moon. And today, the near side of the moon, almost all craters have been mapped. And because we have samples of lunar rocks that are brought back by the Apollo missions, we also know the ages of these craters. And so, if you look at this kind of a graph, you are essentially plotting, the frequency of impact craters, and you're essentially looking at the age of these craters. So what is quite interesting is that most of the impact craters on the surface of the moon are actually very old. And you can see that with increasing age, or from the formation of the moon to the present day, the frequency of impact craters have actually gone down. And around 3.8 billion years ago, there was this little blip, known as the late heavy bombardment, where suddenly, because of the migration of these large planets, you had objects, from the Kuiper belt as well as the asteroid belt that were thrown into, eccentric orbits, and they collided with the surface of all planetary bodies. But the moon is a great, place to work because nothing has really changed on the moon since these craters have formed, right? So, this is essentially what we see on the moon, and this is expected to have happened on all solar system objects. Now, the effects of impacts and collisions on the solar system, the large effects are, if you just look at the planets, you can see them because you have, Mercury, which has an unusually large core compared to the, the size of the planet, and that is primarily because there was a collision of, proto-Mercury with another body that was, quite large in size, and that stripped off a part of its silicate mantle. Then you have, Venus that is rotating, in the clockwise direction, the wrong way compared to all the other planets. You have Uranus that is actually spinning on its side, and you have Neptune that is tilted about 30 degrees. All of these are, the results of planetary collisions in the early solar system. Collisions are also important because, when you look at heat sources in the early solar system, of course, you have the short-lived radionucleides like aluminum-26 or, let's say iron-60. But in addition to that, for slightly larger planetary bodies, which were maybe, a few hundred kilometers in size, collisions between these planetary bodies could have, increased temperatures drastically. And that would melt, silicate rocks and minerals and cause, temporary magma oceans. And that would facilitate, separation of silicates from metals. And this is what is known as core mantle differentiation. Okay, so collisions or planetary collisions are important heat sources. And, today, all theories about accretions of planetary bodies in our solar system essentially invoke collisions. And this is known as the hierarchical accretion model, which essentially suggests that you had simultaneous growth and differentiation of planetary embryos. So at any instant of time from the point you had gas and dust and we started growing these embryos, they were not only colliding with each other and melting and differentiating into a core and a mantle, they're also colliding and becoming larger and larger. So this is a schematic representation where it shows how the proto-Earth may have grown. And the material around a particular embryo, which eventually becomes a big planet, is cleaned up because of the gravitational attraction of this body as it grows. And occasionally, towards the late stages, you might have a collision between a protoplanet and a slightly larger planetary embryo, in which case you might have this. For the Earth, we know that this is how the moon formed. And this was the giant impact, that happened, with the Mars-sized impactor and the proto-Earth, which led to the formation of our moon. And again, using isotopic tracers, researchers argue that this could have happened about 30 million years after formation of the solar system to maybe about 100 million years after the formation of the solar system. Okay. So, and this is just a smooth particle hydrodynamic, kind of a simulation by Asfog and others. And I'll show more about that later. So if you focus on the surface of the Earth today, you'll find, this is a map showing the distribution of terrestrial impact craters, and over 190 craters have been identified on Earth. And on the Earth, you have, the younger craters are preserved much more than the older craters. And so this is a distribution, age distribution that is just opposite to what we find on the moon. But this is primarily because of the preservation bias on the surface of the planet, of our own planet, because Earth is active. We have weathering, we have erosion, we have plate tectonics that is operating, but the moon is frozen still. So the moon, and the picture on the moon is the real picture. The picture on the Earth is essentially, reflects some kind of a preservation bias. And just some images of what craters look like. This is a meteor crater in Arizona, about 2 kilometers in diameter, only 50,000 years old. Then you can see this Manicouagan crater in Quebec, much larger, 72 kilometers in diameter, but also about 200 million years old. And you can see that the rims are quite eroded by glaciation. And then one of the oldest craters on Earth is a Red Throat crater from South Africa, which is 300 kilometers in diameter. And it's about 2 billion years old. But you can see that unless somebody really told you that this was a crater, you would have found it hard to imagine that this was actually a large circular depression. So, the preservation bias is quite evident out here. Now, what really happens during an impact crater? You have a hypervelocity projectile that comes and hits a target, and it sends in shock waves. And so these shock waves penetrate the target and cause fracturing, melting. Of course, there's mixing of material, vaporization, and eventually you're left with a crater, right? So you increase the pressures and temperatures drastically over a very short period of time. And in this diagram, if you look at the shaded region, this is the domain of what is known as metamorphism on Earth. So when you have rocks that are being, subjected back into the interior of the planet and brought up back, that is, terrestrial metamorphism, but that happens over very slow time periods. But on the other hand, soon after a collision, shock metamorphism actually reaches very high pressures, and you can form shatter cones. You form these planar deformation features. I'm going to show you an image in the next slide. You have dielectric glasses and melting. So you can see that the pressure temperature regimes are very high. And just to give you an idea, 1 gigapascal is about the pressure change that happens at every 30 kilometers deep inside the Earth. And so planar deformation features are these crystallographically defined planes that appear after this kind of a shock event. And this is often seen in minerals, which normally don't have these crystallographically defined weak planes, or what is known as a cleavage plane. So quartz does not have, quartz is nothing but SiO2. It does not have a cleavage plane, but if you have shocked quartz, you'll find these kind of planar features developing, and that is a telltale indication of an impact cratering event. You can have shatter cones. You have these aerodynamically shaped glasses, silicate glasses that form because material is molten and it's thrown up, and they cool very rapidly as they spin, and that's why we get these aerodynamic shapes. And often crystals like this plagioclase feldspar crystal has lost its crystallinity and becomes isomorphous, right? Amorphous, sorry. And but the important thing is the impactors, the projectiles that come and hit are rarely preserved at the site of impact cratering. And so the question is, what are really the sources of all these extraterrestrial material that reach the Earth? And if you study the Earth well, you can study the other planetary bodies also, right? So some of the clues, come from these craters, but as I said, the impactors are rarely preserved. So this is, one, a rare example where in this Moroccan crater in Africa, the crater itself is about 70 kilometers in diameter, but what remains is only 25 centimeters of, a chondritic meteorite. We may have heard of this Chicxulub crater, which, it was the smoking gun behind the extinction of the dinosaur 65 million years ago. It is about 170 kilometers in diameter, but what we find is only millimeter-sized fragments of a meteoritic material. Okay, so what are these impactors? Most of these are actually being derived from the asteroid belt today, and in some cases, extraterrestrial material is also derived from the moon. They're known as lunar meteorites, or from Mars, which is known as Martian meteorites. But mostly, material is actually being derived from the asteroid belt. But there is a lot of geochemical heterogeneity between, within, the material that is today present in the asteroid belt, and some of these are remnants of, planetesimals, broken up planetesimals, which never saw melting. That means we call them, primitive material or chondrites. And some of these, material in the asteroid belt are actually remnants of broken up, planetesimals where planetary differentiation had already occurred. That means that planetesimal already had a core and a mantle, right? And those we call as differentiated materials. And so these meteorites we have at our disposal, and they have very distinct chemical and isotopic characteristics. So this is what we use to understand the signatures of these extraterrestrial objects for cratering. Another important aspect of cratering is that it exposes subsurface material, right? So for planetary exploration, we may have noticed that almost all the rovers that actually land on all these planetary bodies are actually forced to land in craters, because that's where you have a subsurface material being exposed. And so in the future also, when we bring back samples from planetary bodies like the Mars, or even maybe Venus at some point of time, we will actually have impact breccia material and soil, right? So the questions related to impact cratering would be, how is the chemistry of the target rock modified by impact cratering, and could the compositions of the impact melts that are produced as a result of impact cratering provide insights into compositions of subsurface material on the target planetary body? And with that, we will take a look at how this is done. We obviously collect samples for terrestrial craters. We measure the geochemical and isotopic compositions in a laboratory, and these are some images of a clean laboratory that I have. In addition, we have mass spectrometers like this ICP-MS and the TIMS, which is what I used to, my students basically used to determine the compositions of samples, and then we interpret the data in terms of process and time, and finally get to the source and the composition. So if you look at India, we have 3 craters essentially. These are the 2 best studied craters, of which in today's talk I'll be talking about the Lunar crater. This is in the Buldana district of Maharashtra, very close to Pune actually. And today it is actually filled up by a lake. It's called the Lunar Lake. And much of what I'll be presenting right now is from a paper that my student Rahul Das Gupta had published a few years ago. And so this is a very well preserved crater on basalts, only 2 kilometers in diameter, a simple crater. And it's actually hosted on the Deccan basalts, right? And this is one of the unique craters on Earth, which is actually hosted on basalts. And this makes it a planetary analog for craters on Mars or even the Moon and Venus, because most of these planetary bodies actually have basaltic crusts. And we have determined the ages for these craters. This is about 500,000 years old. And as part of the study, we collected these breccia samples, these rocks. We have the target basalts. We have some weathered material. This is a soil called red bowl. And we also have soil samples. This is just a map of the Lunar crater and locations of all the samples. What we're going to focus on as part of this study is essentially some of these glassy, spherical and non-spherical glassy objects that we separated from the soil. And these are just some examples. You can see that they have these aerodynamic shapes. So they are clearly molten material that was thrown out into the air after this impact cratering event, and they eventually landed there. And so those are the ones that we want to study as part of what I'll be presenting today. And we just measure their concentrations of different elements and isotope ratios. In this case, we actually collaborated with some folks in Belgium, because these are so tiny that you cannot really dissolve everything. So you actually do a laser ablation study. It means you can go to spot sizes that are a few microns and get the compositional variability within the single glossy beads. And the first thing that we have to do for any terrestrial sample is to basically correct for possible chemical effects that have happened after the main event that we are trying to address. And in this case, this crater formed 500,000 years ago. So over the last 500,000 years, the samples out here have been exposed to surface conditions in Earth, right? So, you may have had what is known as alteration. So we screen chemically for alteration by using ratios of elements that are fluid mobile versus elements that are non-mobile. So sodium, calcium, potassium, these are fluid mobile. Aluminum is not. So a ratio of this, elements gives us what is known as this chemical index of alteration. And low values of CIA basically tell you that things are not altered, and high values means they are altered. So the basalts are these black squares for the rest of the presentation. These are the target rocks. We have the soil, which is expected to be weathered, and that's this red square out here. And then we have some impact breccia samples. These are whole rocks. These are not these tiny beads. These are plot somewhere out here, these brown circles. Then we have all of these spherules. And you can see that there are 2 groups of spherules that we label. One that basically shows very low values of CIA. So that's the group 1 spherules. And then the group 2 spherules in blue out here are the ones that have high CIA values, suggesting that there is some alteration, which is not related to the impact cratering process. If you look at the group 1 spherules only, the least altered ones, and you look at the concentrations of some of these transition metals like nickel and chromium, you will find that there are 2 groups. There is this one group of samples with very low nickel and chromium, while the other group of group 1A spherules actually have higher concentrations. And so for the rest of this talk, I'm going to call the group 1A spherules as the ones which have these higher nickel concentrations and chromium concentrations and magnesium concentrations. And then the other set of group 1 is 1B, which have lower concentrations of nickel, chromium, and magnesium. And so if I had to show the CIA diagram again, you have the group 1As out here, the filled blue and the filled green at the group 1B, and the inverted blue triangles at the group 2 triangles. So other than this red bowl and this, maybe these inverted triangles, all the other samples are unaltered. So we can now, study these samples to basically go back to the real picture. And that is what we do. We look at concentrations of nickel and chromium. And we look at an enrichment factor. So we're basically normalizing the concentrations in the samples to what is expected in an average basalt, because that's the target rock. So with respect to the target rock, how is the concentration changed? And this is the basalt, this is the breccia, the red ball out here. Quadratic meteorites plot way in that direction. Okay? And so if you look at the spherules, you can see that many of them actually show some indication of enrichment in nickel and chromium, and they move in the direction of chondrites. So this gives you a first hint that maybe some of these spherules are actually carrying signatures of the impactor itself. The green triangles out here, which are these group 1b spherules, interestingly, they overlap with compositions of the impact breccia and also this UCC, which is an average upper continental crustal composition. Okay? We further look at concentrations of trace metals and what is known as platinum group elements, iridium. And why we choose these elements? Because their concentrations, like the ones in iridium, are very low in crustal rocks, because these are highly siderophile, that means iron-loving elements. And if you look at the bulk Earth, much of iridium is actually sitting in the Earth's core, and we don't have access to samples from the Earth's core. So whatever is you find on the surface of the planet, if these are significantly high, they're actually showing you signatures of extraterrestrial inputs. And so the Deccan basalts and crustal rocks are up here. So you can see very low concentrations of iridium, and chondrites are up here. So this is the log scale. So you can see they're way up there. And you can create simple mixing diagrams to basically infer that indeed some of these glossy spherules carry signatures of a chondrite-like impactor. And you can do mass balance calculations to suggest that maybe 1 to 8 to 8% of the composition is actually being derived from the impactor itself. Rest of it is actually a result of melting of the target. Now, we can consider other tracers like rare earth elements, or the lanthanides. And these are the black squares are again the basalts, the target, this is the soil. And with relative to the basalt, which is now being shown here by these shaded diagrams, you can see that the impact breccia have slightly enriched in the light rare earth elements, and maybe some of these large iron lithophile elements. And then you look at group 1A, has a very significant lead depletion out here relative to the basalt. The 1B spherules again have these enrichment in large iron lithophile elements and an niobium tantalum depletion. And then the group 2, which is slightly weathered, the coherence in their compositions is slightly less, which is consistent with their alteration post factor and post impact cratering. So if you try to look at all the patterns that you see out here, you basically can rule out the contribution of the red ball to any of these impact types. You find that in the group 1A spherules, there is a lead loss, which lead is a volatile element. So maybe this is related to the impact cratering event itself. And then you have the impact breccia and the group 1B spherules, which show these niobium tantalum anomalies, suggesting that there is incorporation of a third component. This is a felsic, that means something that is high silicon, not the basalt itself, but a felsic crustal source. And we wanted to investigate that a little further. And shown here are ratios of some transition metals. And what we find is the basalts are out here. This is an average upper continental crust, which is typically expected to be a granitic or granodioritic in composition. This is the impactor or a chondrite. So you can see that the group 1B spherules, they plot on a mixing line between a granitic end member and a basalt, and it doesn't contain any signatures of this impactor. And this is true for multiple element plots, right? And so they're carrying signatures of a granitic basement that is below the Deccan traps. So the Deccan actually erupted on the Indian continent, right? So while we see basalts only on the top, and we don't see any other rock type around the Lunar crater other than the basalt. But it seems like during the crater formation itself, some of the granites were exposed and melted, and that signature is basically preserved in some of these spherules. On the other hand, the group 1A and the group 2 spherules actually have higher nickel chromium ratios, nickel cobalt ratios, and they move in a trend that is kind of towards an average chondrite. So they are the ones that actually preserve signature of the impactor, while the group 1B actually preserves signature of the basement. And the shaded region is essentially some data that was published earlier, although not plotted in exactly this kind of a diagram. But clearly, you can see that these tiny glossy beads, which are just a millimeter or so in diameter or even less, basically carry signatures of the basalt, carry signatures of rocks that are beneath the basalt. That means the basement rocks, as well as signatures of the impact, right? So we next wanted to look at some isotopic compositions. What we are using out here is the decay of 147 samarium to 143 neodymium. These are lanthanides and over a half-life of about 107 billion years, so very long-lived isotopes. And then 87 rubidium decaying to 87 strontium by beta decay, again a half-life of about 49 billion years. The take-home message from this kind of a diagram is the basalts are out here, right? So if you melt a basalt, the impactites should actually, the melt rock should actually look like a basalt, right? But what you find in the spherules, which are shown by these vertical diagram lines, or the impact breccia, is that they have higher values of 87, 86. That means radiogenic strontium. And this is indicative of involvement of granites. Now, granites are, again, the basement rocks beneath the basalt. So while the rocks are basaltic, their composition clearly tells us that there is incorporation of a granitic signal. That means it is not just the basalt that melted during impact, the granite beneath the basalt also melted. So we have isotopic evidence for basement melting out here, and we can take it a step forward by looking at n-member compositions and try to calculate the contribution of the granitic basement. And this is about 27 to 8%, up to 27 to 8% in some of these brecciated material. Let us now take a look at another aspect of impact rating, and that is, we look at volatile elements and their concentration. So we are focusing here on elements like lead and zinc. Both of these have these condensation temperatures that are reasonably low. That means if you have a nebular kind of a gas cloud and you're cooling it, the elements that basically prefer to stay back in the vapor phase for a long period of time are volatile. So that means they will only condense into solid phases at lower temperatures. On the other hand, if you have elements that are cooling out and forming the first solids, as you start cooling a nebular gas, those are refractory elements like calcium and aluminum. So we are looking at these moderately volatile elements, and what we find is relative to the basalt, which is shown here by these horizontal and vertical lines. You can see that in these spherules, you have a depletion in both lead and zinc. That means during the process of impact cratering, we have lost some of these volatile elements. We can consider concentration. So while most of these are actually being lost, in some of these spherules, you find that the basalts are somewhere out here, these black squares, but some spherules seem to be showing higher zinc concentrations than the target itself. And this is possible only if you have a silicate vapor cloud that formed and recondensed rather rapidly, such that the volatile elements that are part of the vapor material are now being enriched in their condensate. And so this is evidence for condensation from a volatile rich vapor. And we also find that when you're looking at concentrations of zinc being reported by other researchers, although this was not really investigated along those lines, we also find that there is enrichment of copper, which is again another slightly volatile element. And some of these spherules actually show enrichment in copper. So the enrichment factor of copper and zinc seem to be correlated, suggesting that there is widespread evidence for condensation from a silicate vapor that actually formed soon after this impact cratering event at Lunar. Now, the next question that we wanted to ask is there any relationship between the chemical composition of these spherules that we've discussed thus far, as well as the non-spherical impact glasses, which is the acronym NSIG is for that? And is there any relationship between the composition and maybe their shapes and sizes? This is an open question. And so what we did is we picked up some of these material, and we tried investigating these samples using X-ray microcomputer tomography, or micro CT as we call it. And what we find out here is some representative diagrams. On the left, these are some micro CT images of these spherical glasses. And what you find is that they have a uniform shade of gray. Occasionally, you will have these darker shades, which are nothing but air bubbles, but the composition is rather uniform. In contrast, when you look at these non-spherical impact glasses, now again, note the bars out here. These are about half a millimeter in length out here, and the longer part of it is possibly 1.5 millimeters or 2. But what you find out here is, in addition to some of these air bubbles, you have these whitish specks. So when you have these white specks, it basically, this is just telling you that these are more metallic material that is actually trapped within this non-spherical impact glasses. So if you look at some of these representative micro CD images, one can conclude that while the compositions of the spherical impact glasses are more homogeneous, you have a lot of heterogeneity, compositional heterogeneity within these non-spherical impact glasses. And so you can also calculate, during this micro CD measurements, the volume, the total volume of these air bubbles of the pores that are actually found within these spherical and non-spherical impact glasses. And you find that the longest diameter of the NSIG, that means the bigger ones, the bigger impact glasses actually have larger fractions of air bubbles trapped in them. Okay, so this somewhat could reflect the physical dynamics of this melt vapor plume and how some of the volatile elements might actually be trapped into these quickly quenched silicate melts. What we also find is another interesting aspect, and that is, if you look at the nickel by chromium ratio, the higher values are essentially suggesting more incorporation of the impactor material, which is the chondrites. We find that there is a strong negative correlation between the nickel-chromium ratios in these spherules and their average diameters. Now, obviously, we have binned them into different diameter pools, and we are looking at the average nickel by chromium ratios in material from this particular bin, but the correlation is quite strong. This is suggesting that the impactor signatures, which means that the high nickel by chromium ratios, are mostly preserved in the smallest of these impact material, or the spherules. And so these spherules most likely are, again, vapor condensates, because you can form spherules either by quenching the melt or by recondensing the vapor. And it is kind of well understood that the impactor is almost always vaporized very quickly. And so if you have impactor signatures, those are really recondensates from the vapor plume. And so again, this kind of a mixed signal from geochemistry and the morphology of the spherules basically reflects physical processes that are actually taking place within the vapor plume itself soon after an impact radiating event. And so if I had to sum up what I've shown you in terms of impact craters, especially for the Lunar, we find that the impactor, even though it's not preserved at Lunar, definitely was a chondritic meteorite-like parent body. And we find that in some of these glassy melts, you have up to 8% contribution from the impactor. And the impactor signature is almost preferentially preserved in the smallest of spherules, which means that these spherules were most likely, recondensates from the vapor cloud. And then there are other spherules which preserve signatures of the granitic basement that is beneath the Deccan basalts. You cannot see them on the surface, but this spherules preserve their composition, and isotopic data suggests that you can have up to 27% contribution from this basement rock. And we also find that excesses of copper and zinc concentrations in some of the spherules could also tell us something about recondensation of the vapor cloud. So from these tiny sub-millimeter sized objects that are collected from this crater that is about 2 kilometers in diameter, one can tease out a lot of information about crater dynamics, as well as what is actually beneath the rocks that are exposed on the surface. So these have implications for planetary studies, because in a decade or two, when we finally get samples from the surfaces of planetary objects, planetary bodies, a lot of it would be soil, like for example the regolith on the moon. And these soils are will have a lot of these spherules and non-spherical impact glasses, which have been thrown from craters all around the surface of these planetary bodies. And so analysis of these tiny glassy objects might actually have very big implications in terms of understanding what's the nature of the crust, what was the nature of the impactor, and so on and so forth. So I will now transition to from a 2 kilometer diameter craters to more planetary scale events. So I will essentially focus on the aspect of volatile loss and I'll provide you with a couple of examples from study of lunar rocks and some specific meteorites. So let's start with the moon. And we all know today that the moon essentially formed by this giant impact where a Mars-sized impactor called Theia collided with the proto-Earth. And this could have happened about 30 million years after the first solids started forming in our solar system. And this is again, I've shown one part of this diagram earlier. These are smooth particle hydrodynamic simulations, suggesting that much of this impactor essentially got assimilated within the proto-Earth, and that led to an increase in the size of the Earth. But in addition to that, you actually formed a silicate vapor cloud around this proto-Earth, which eventually condensed to form the moon. And this model is now reasonably well understood. Of course, modelers are trying to tweak how we can actually look at the angular momentum of the Earth and the proto-moon system, and how does it have to do with the spinning of the proto-Earth and the compositions of lunar rocks and their similarity with terrestrial rocks. And that is what I wanted to show you in the next slide. One very important aspect is that the Earth and the moon basically have a lot of compositional homogeneity. So this has been known for the last almost 35, 40 years. And when you look at oxygen isotopic compositions of the rocks, not only from the Earth, but for meteorites and objects from all parts of the solar system, all terrestrial samples plot on this dashed line, which is known as the terrestrial mass fractionation line, which is defined by the mass difference between 17 and 16 oxygen and 18 and 16 oxygen. Now, most meteorites, they plot away from this line. You have Mars and Moon that don't plot exactly on this line, but have similar slopes. The only other planetary object whose samples plot on this terrestrial mass fractionation line is that of the Moon. So this was one of the first evidences suggesting that maybe the Moon actually formed out of the Earth. And subsequently, with improvements in mass spectrometry, we've now been able to measure isotopic compositions of other heavy elements like silicon out here, magnesium out here. And again, the Earth and the Moon basically have the same silicon isotopic composition, magnesium isotopic composition, and the list goes on. So it is quite homogeneous. Now, in this particular talk, we are focusing primarily on volatile loss. So what we need to do is pick our element or the tracer very carefully. And so if you look at the periodic table of elements, you can classify the elements based on their condensation temperatures, from their thermodynamic properties. And what we're going to do is we talk briefly about zinc and copper. Some of them are moderately volatile, but for the rest of the talk, we'll talk about potassium, which is also a moderately volatile element, which means that if you have a solid and you increase the temperature quickly, this will be in the gas phase. If you have a gas and you condense material, it will prefer to be in the gas phase for a long period of time before it gets incorporated into solids. So we'll look at the isotope ratios of potassium. The potassium has 3 isotopes, but we're going to be focusing on the ratio of 41 potassium and 39 potassium. We use this delta notation, which is just this particular ratio in your sample, relative to the same ratio in a standard that is being measured by multiple groups. And we express this deviation from the standard in parts per 1,000. And so parts per millennia, which is where this per mil sign comes in. And so it was expected that because the Moon is known to have lost a lot of volatiles in terms of its geochemical composition, this is a model curve which was expected for the potassium isotopic composition of all these planetary objects. But in the mid-90s, there's a paper by Humayun and Clayton where they could find no difference between the potassium isotopic composition of the Earth or the Moon or these other planetary bodies. These are Martian meteorites, chondrites, so on and so forth. The only thing that they found is that some lunar soils, they basically have lost some of their lighter isotopes. Hence, their delta 41 potassium value is slightly higher. And this, they suggested that this is a result of micrometeorite impacts that is constantly happening on the Moon, and that can perturb the composition of the lunar soil. Now you fast forward, about 30 years or so, and you now have this new generation of mass spectrometers called the multi-collector ICP-MS, the inductively coupled plasma mass spec. And this paper by Wang and Jacobson demonstrated for the first time that the moon indeed has higher values of delta 41 compared to the Earth samples. So this is the first difference that you started finding. For all other isotope systems, things were pretty much constant, right? But what it means is that the lighter isotopes of potassium have been lost. And so this is consistent with the theory of volatile loss on the moon, during formation of the moon. But one can also look at it from a different angle. You can look at it from a theoretical point of view and say that if this partitioning of isotopes, potassium isotopes, was happening in vacuum, which is what is expected for the moon, then what should be the relative difference in the ratios between Earth samples and lunar samples? The difference should have been significantly higher than this difference of about 0.4 or 0.5 per mil, which suggests that when this fractionation was actually taking place between the Earth and moon, this was not happening in vacuum. So you can constrain the pressures that were actually existing when the proto-lunar disk was actually existent. And people have suggested that we actually have pressures of up to 10 bars when actually the moon was forming and when this kind of a potassium isotopic fractionation was taking place. So this kind of puts in some constraints on the pressure conditions. It also tells you how far away from the Earth, from the Roche limit of the Earth, the proto-moon actually formed. Because if it formed significantly far away, then the pressures would have been much lower. So it kind of puts in some constraints as to how far away the proto-moon actually formed from the proto-Earth. So this is quite interesting. You not only show that there is volatile loss on the moon, you also demonstrate that the formation pressures were significantly high. Today, the surface pressures of the moon are extremely low, right? Now, of course, one can look at lunar rocks in a slightly more detailed manner. Of course, when all the lunar samples were returned from the Apollo missions, what we found is that in addition to basalts, you also have rocks that are enriched in lighter minerals, lighter elements called anorthosites. Then you have minerals like ilmenite, which is an iron titanium oxide. And so this idea of a lunar magma ocean actually came up, which means that because of the rapid accretion of the moon, you release a lot of gravitational potential energy, and of course there was a collision, so it led to large-scale heating of the proto-moon, which would have melted the greater parts of the moon. And as the moon cooled down, you started crystallizing new minerals, right? And the first minerals that formed are these common rock-forming minerals known as olivine and orthopyroxene. These are mostly made up of iron and magnesium, so they are dense. So they settle to the bottom of this magma ocean. And then you crystallize lighter elements like plagioclase and clinopyroxene. Plagioclase is very light. That floats up, and today we have an anorthositic crust on the moon, the lunar highlands, where the Chandrayaan-2 was supposed to land. And that is actually made up of lighter material. Subsequently, you crystallize what is known as ilmenite, but because ilmenite is dense, there is this theory of a lunar mantle overturn. But the point is, today we have samples of different lithologies of the moon. We have the basalts, we have the low titanium and the high titanium basalts of the moon. We have the creep-related basalts, which are enriched in the rare earth elements in potassium and phosphorus. And then, of course, the lunar anorthosites. So, last year, there was this very interesting paper, again, a much more detailed paper on potassium isotopic composition of different types of lunar rocks. So, this is again the delta 41 potassium, and these are the basalts, the high titanium and low titanium basalts, similar composition. But then you find some lunar rocks, the anorthosites, which are these light material, which have very low potassium in them. They are the ones which are enriched in the lighter isotopes. That means that delta 41 is actually low. And then there are some samples that have lost some of the lighter isotopes, and hence their delta 41 is actually heavy than the basalts. So this is again, explained by volatile degassing. So if you have degassing of the lunar magma ocean, then potassium, along with some other phases like chlorine, might actually evaporate from the system. And during evaporation, there is also isotopic fractionation, because the lighter isotopes have a lower 0-point energy. So the moment you supply some energy, the lighter isotopes go into the vapor phase. And so the residue, which is the rock, is not enriched in the heavier isotopes. Now, what about these samples which are enriched in the lighter isotopes? This is again, proof that some of the vapor phase, which actually went up, recondensed in other parts of the lunar surface, and those are the places where you actually have enrichments of the lighter isotopes. And this is very well demonstrated for these lunar rocks. So we not only have evidence for degassing, we also have evidence for recondensation on a larger planetary surface like the moon. I've shown you similar examples of what happened in a single crater on the Earth, which is just 2 kilometers thick, but this is happening on a planetary scale. So the last 3 or 4 minutes, I'd like to talk to you about potassium isotopes only, but let us not just focus on the moon, but focus on other planetary objects for which we have samples for. And for the first part, let us focus on data that is now published for Martian meteorites. We already talked about lunar samples, which are in green, and then we have samples from these meteorites called HED. They're Howardites, Eperites, and Diogenites. But these are very well pinpointed. Their sources from this large asteroid called 4 Vesta, which is part of the asteroid belt. You can see that if you look at the composition of the Earth, that's somewhat heavy out here, somewhat low, sorry. And then Martian samples have a slightly higher value. Then comes the lunar sample. Then comes the Vesta sample. So there's somewhat of a trend out here, right? But what does this trend really mean, and does it have any implications? So in this paper, which was published a few months ago, this group basically showed that this potassium isotopic compositions of samples from Vesta, Moon, Mars, and Earth are negatively correlated to the radius of this planetary body. They're also negatively correlated with the log of mass of the planetary body. And more importantly, they're also negatively correlated with the surface gravity, of course, because the size is smaller, and the escape velocities. So they're hinting that this loss of the lighter isotopes, which makes the delta values higher and higher, is actually linked to the size of the planet itself. And another very interesting point is that if you look at the average H2O concentration in rocks, so these are not free water, but bound water. And if you look at the concentration of water in parts per million in average Earth rocks, average Mars rocks, average rocks from the moon, and 4 Vesta, there is also this negative trend that you find with the delta 41 potassium values, which means that we all know potassium is volatile. And this volatility or volatile loss has got something to do with essentially the size of the planet. That means essentially the planet itself. But we take another volatile component, which is water, and we find that indeed, both volatile loss not only affected potassium, but also affected water. So these potassium isotopic systematics of these large-scale planetary bodies seem to be essentially pinpointing in a planetary scale volatile loss. And it now has very important implications because this seems like a very powerful tracer to actually pinpoint how much volatile loss would have happened in other planetary bodies. Now, this essentially is for planetary bodies that are differentiated. That means they have a core and a mantle. What about the more primitive objects? And by primitive objects, I mean that these are remnants. These are meteorites that are remnants of broken up planetesimals, and those planetesimals never really had enough heat in the system to actually melt and differentiate. And so these are called Quadratic Meteorites, and then there are different classes. There are enstatite chondrites called EC out here, carbonaceous chondrites, and then the ordinary chondrites. And you can see that there is quite a large variability in the potassium isotopic composition of these primitive objects relative to this gray bar, which is where the Earth samples plot. And in addition, the potassium isotopic composition seems to be negatively correlated to the potassium concentration itself. And this is normalized to concentrations of CI chondrites, but just as the way of representing data. So what it means is that if you have low potassium in your system, that means potassium has been lost as it is a volatile element, you also lose the lighter isotopes, which is expected. So this could be a volatility trend even for these primitive planetary bodies. However, one has to be a little cautious because potassium is also fluid mobile. So what if you actually had aqueous activity on some of the planetary bodies which are represented by these primitive meteorites? And maybe this trend of potassium loss is not just lost by volatility, but it's lost by, let's say, aqueous activity. And in which case also, we see it on the Earth too, that during weathering, you have fractionation of potassium isotopes. Nevertheless, it gives you a very interesting trend. And this is where, there's a student of mine, Dipankar, who did his master's thesis with me. He had analyzed, he had studied essentially these 3 meteorites that fell in India, all in Assam. This is Dergaon, Pengari, and Mahadevpur. These were collected soon after they fell. And we sent some of these samples to Kun Wang's group, who has pioneered this potassium isotopic measurements. And what we find is that these are all ordinary chondrites. Dergaon's composition plots out here, the red circle, Mahadevpur is this green circle, Pengari is this blue circle. And you can see that compared to all the other published data for ordinary chondrites, these values are even higher. That means the lighter isotope loss in these 3 meteorites from India is significantly higher than what has been reported for ordinary chondrites collected from other parts of the world. In addition to the same diagram, and if I look at the potassium concentration plot, I do see this negative trend for these 3 circular samples. The symbols out here, this is Dergaon, this is Pengari and Mahadevpur. The negative trend is there, but they are not as depleted in potassium as the other samples. So this still needs a little bit more work, but it seems like the Indian meteorites are a little more pristine. That means they have not really been altered by aqueous activity as much. So the potassium loss is less, but the isotopic fractionation is quite severe. So this could again represent either volatile loss on the parent body of these meteorites. And so essentially this volatile loss is all linked to planetary collisions. So these have affected the moon, these have affected the parent bodies of all these meteorites, which are now remnants as little asteroids within the asteroid belt. And I've also shown you that volatile loss can happen when you zoom into a simple crater even on the Earth. So with that, I would like to leave you with some take-home messages that say that, look, planetary collisions were the key features to accretion and evolution of planetary bodies. From the terrestrial craters, studies, geochemical and isotopic studies can tell you something about the nature of the impactor, which is no longer preserved. We can talk about contribution of the impactor to the impact melts. And you can also infer maybe the subsurface rock type composition at the target site. And this is the third point, is essentially very important for when we go to other planetary objects and study impact craters. We also find that the morphology of the crater of the spherules and their compositions, they basically talk about volatile loss and recondensation. So it tells you something about the dynamics of the silicate plume that is that forms after an impact cratering even. And if you look at volatile elements like potassium, and especially their isotopes, you can basically unravel complex surface processes related to volatilization and recondensation, as well as maybe aqueous activity on a planetary body on the moon, as well as parent bodies of different classes of meteorites. Now, of course, the aqueous activity is possibly not relevant to the moon because the moon is very dry. But definitely it could have happened in, let's say the parent bodies of some of these carbonaceous chondrites, like the carbonaceous, some of these chondrites, specifically the carbonaceous chondrites, which actually have some water in them. So with that, I'd be happy to take some questions.
Thanks very much, Ramanand, for this absolutely fascinating talk. I mean, this is a wonderful, and also as far as methodology is concerned, there are some great parallels in how people who do stellar and galactic analysis of the chemical evolution study very similar things, the same kind of isotope and elemental ratios and stuff. So people are raising their hands and using Zoom hands. Before Shanjit, let me just quickly ask you one question. See, very fascinating the variation of the signatures that you're getting from various places in the moon, but the southern hemisphere of the moon is largely unexplored to some extent, and this is one of the reasons why Chandrayaan-2 wanted to go there, and the future mission together with Japan is trying to land. What is the expectation of what you'd find from the craters and other non-Mars rocks down there in the southern hemisphere compared to the northern hemisphere? Is there any qualitative difference?
Well, I think even though some of these missions that you mentioned are mostly targeted, or they're being labeled as water on moon, but one is to realize that these permanently shadowed regions on the moon are essentially, they're permanently shadowed because they're part of craters. So if you have, these basin-like depressions, some of these basins, as I said, they can have raised rims, they're complex craters or ring-like structures. And that basically prevents, and of course, because they're in the southern, almost close to the poles, and the angle at which the sun rays actually shine, it is actually material in these craters that never see sunlight, and that's why those are the parts where maybe you can preserve water in its ice form. So the craters are everywhere, and actually even the permanent shattered regions are there primarily because of craters. Now, when it comes to the lithology, the northern and southern hemispheres, there is some difference. While most of the surface of the moon is primarily basalts. Now, of course, all of you are sitting on the Deccan basalts, but basalts, if you know, the oceanic crust on the Earth is all basalts, right? So if you take any rock sample from the oceanic crust, you're essentially going to get basalt. And so basalts are, very common partial melting products of any silicate mantle. So even the Earth's mantle is made up of silicate, right? Silicate rocks and minerals. And because you're partially melting them at different times, that's why magnetism happens. The melt that comes up is primarily a basalt or a slight derivative of a basalt. Now, even for the lunar surface, the fact that you have Mare basalts almost everywhere is a lot of it is, after cooling off the magma ocean, but a lot of it is also because of this cratering activity. So the moment you had these large impacts on the moon, and all of these are preserved because the moon does not have an active surface. So you actually caused a good bit of decompression or melting right away. So because you have hit it with an impactor and you've kind of dug up a lot of material, suddenly the overburden pressure actually goes down. And so if you bring material just by reducing the pressure adiabatically, even without introducing a lot of temperature or heat in this case, you can actually intersect the solidus. Now, as we all know that when you look at these rocks and minerals, they don't have a single melting point. They have either solid solutions or so they have a solidus temperature. So you can intersect the solidus, and that's why you have melts. So basalts are important, but the southern part of the moon will also have some of these anorthositic materials. You can expect some of them, and variations of different minerals. And in some cases, there were these remote sensing studies reporting chromites, which are these chromium oxides, which were earlier not found, not detected in the lunar samples that were brought back. So I think there's a lot of surprise element that can be there on different parts of the moon, the way you explore it. And so understanding the mineralogy, the rock types, these are key. In addition to that, shock features, because whatever you collect from the moon will have, I didn't show you, some aspects of Raman spectroscopy because, each mineral has its characteristic Raman peak. But the moment you shock them, that means you expose them to high pressures for a very short instant of time, the characteristic peaks, they either shift a little bit or they become wider. And there are these calibration studies done in labs where if the pressures are a few gigapascals or more, then the characteristic peak is completely gone. And so, I've done some work on this, early on, but all of this is expected on the moon. So in addition to, the nature of the Raman peak can also tell you the shock pressures. Now, the shock pressures in turn will tell you about the size of the impactor that may have hit the surface of the moon. So, whatever data we generate from these kind of missions, I think the way, there are different ways of interpreting the data. And I think, all of it is equally exciting. But right now we are all focused on water primarily because of societal reasons, right? Because we would like to understand, water being present somewhere else. But I think there is a lot of other information that will also come out.
Great, thanks. I think Shonjit's hand was up. Shonjit, go ahead. Do I need to unmute you? Possibly. I've unmuted you, Shonjit. What happened? Yeah.
Yeah, I think you can hear me now.
Yeah.
Very nice talk. I just wanted to ask you one thing. So if I understood correctly, in the lunar crater, the group 1A and group 1B give you the properties of the impactor and the initial surface respectively.
Right.
Now, but then there are many craters on the Earth, right? So now, do you see any similarities between the group 1A spherules at different sites, but at the same time? Let's say that 500,000 years ago, all the craters that you have, and you compare all the properties of the spherules. then that can tell us about something about the demographics of these impactors in the solar system and how they evolved with time. Like if you go to the past, maybe something.
Okay.
Yeah.
I get your point. So, okay, the last part of your question is the key, and I'll come to that. But see, this group 1 and group 2 is a classification that is being done by us specific to this particular crater. Okay. Now, when we look at these glassy objects, their composition obviously will depend on the target, right? So, and as I said, out of the 190 impact craters, there are only 2 or 3 craters that formed essentially on basalts. So the Lunar crater that way is very unique, because it's purely on basalts and it's very accessible. There's one in Siberia that nobody can almost access. So that's why the composition of these spherules will vary from one crater to another crater, even though, let's say, the cratering happened at the same time. Now, the composition of the spherule has 2 components. One is the target rock, and the other one is the impactor itself. And that is, I think, the main part of your question. And that is a very relevant question. And if you look at the the tracers that we are using, these nickel by chromium ratios, nickel by cobalt, and nickel by chromium. I have just shown you the average composition of these chondritic meteorites. If you look at the average compositions of these HED meteorites, which are coming from Vesta, or let's say some of the Martian meteorites, they all have slightly different compositions. So, if you look at this specific diagram where I looked at Iridium, I'll come to that. We choose the tracers carefully too. See, as I mentioned, continental crust, right? This is an average value of continental crust everywhere. It has very low concentrations of iridium. These are some basalts, an average Deccan basalts. You can see that the concentrations are very low. So if I take a target rock that is not a basalt, let's say I had some sandstone, in the United States, on which, let's say, there was a crater that formed, 500,000 years ago. The concentration of iridium, in those rocks would also be very low. Now, remember, this is a log scale, right? So you might have some fluctuations out here, but still, I will be able to characterize, the nature of the impactor by, the mixing is essentially controlled by this end member, the chondritic composition out here. And if I plot iron meteorites out here, iron meteorites are nothing but, they are remnants of the cores of Glochina planetesimals. And on this diagram, let me go back to my pointer one more time. Iron meteorites, I've not shown it, they actually have a composition that plots somewhere out here. Okay. So, even though the crater is actually forming, the multiple craters are forming at the same time, they need not, the melt products from these cratering events need not have the same composition, primarily because the target rocks can be different, and also the impactor might be different, or they might be of a different class. Okay. Now, the last point that I want to make out here is that if you look at the collection of meteorites that we have at our disposal, globally, these are mostly preserved in museums and all of that. Most of the chondritic meteorites that are very common, they're called ordinary chondrites. And the name ordinary chondrites essentially came because this specific class of meteorites are the most common ones that have actually hit the Earth. The enstatite chondrites, or the Martian meteorites, and the carbonaceous chondrites are significantly rare. So if one has to, even though the craters are obliterated on the Earth, some of the old craters, one might argue that most of the impactors that actually hit the Earth, over the last, let's say, couple billion years or even 4 billion years or so, would have possibly originated from a very similar location within the asteroid belt. Now, there are researchers who look at which part of the asteroid belt is actually supplying, many of these, meteorites. And I cannot, I don't want to give you a wrong answer out here, but there is some research that is actually going on along those lines. That what is basically the source, which part of the asteroid belt actually, provides most of the impactors for the Earth. Okay. So anyway, so the long story short out here. Compositions of spherules from different craters, even though they're of the same age, need not be the same, primarily because the the target rock composition can be very different, and the impactor. Okay, but for the Moon or Mars has a much simpler, crustal structure. It's mostly basalt. So there, in the future, if we basically get spherules of different types and we find differences in composition, it will tell us about something about the impactors. And if we can date those rocks on the surface of Mars, we might be able to create a history of how the sources of impactors may have changed on a planetary object.
Okay, great.
Thanks. Let's go to Shukanta next. Shukanta, you can unmute yourself.
Yeah, nice talk again. I have a related question, but it's more geared towards the giant impact hypothesis. And I was wondering, how are you able to date it relatively precisely? I mean, I'm guessing, of course, the craters on Moon help in dating things. Clearly, the collision would have reset some radioactive clocks or isotopic clocks. On the other hand, Mars may not be a great reference, even though you showed Mars and Moon on the same plot in that oxygen isotope graph.
Yeah, Mars is a little higher, but yeah, very similar. Yes.
Right, but yeah. So, and of course, volatiles could also be used. But how do you obtain the kind of precision I think I heard?
Sure.
Yeah.
So what is done out here is, we use these short-lived radionuclides. And so let me take a step back. When we look at these radioactive systems, like, samarium-147 to neodymium-143, or uranium-238 to 206 lead, things like that. We are basically, there are two things that affect, the isotopic compositions. One is the elemental ratio of the parent nuclide and the daughter nuclide. So the uranium by lead ratio, or the samarium by neodymium ratio, the elemental behavior is one thing that is important. The second thing is time. Of course, if I have a long-lived isotope system, the daughter growth will happen only over time, right? So there are two ways in which the isotope ratios change. So because we are trying to understand when the moon-forming giant impact happened, and we know that created a magma ocean, and that is linked to, let's say, core formation of Earth. So the nuclides that were actually chosen are hafnium and tungsten. So there is this 182 hafnium, which has a very short half-life of only 9 million years. And that decayed to 182 tungsten, again, by beta decay. So typically, we know that after 5 or 6 half-lives, it is almost impossible to, for the parent to have, of course, it's an exponential decay, but because of instrumental, uncertainties, beyond 5 or 6 half-lives, you really cannot detect the presence of, some of these short-lived radionuclides. So people looked at, tungsten isotopic compositions of, Earth material, and they also, measure these tungsten isotopes in the moon. So imagine what happened when this magma ocean kind of a scenario was there. The iron, this melt, this iron-rich metal was sinking through the silicate, going to the center part of the Earth, right? At that point, the melt and the solids are in equilibrium. After a certain instant of time, when the core has completely formed, it has taken with it a lot of these metal-loving elements. So tungsten is extremely metal-loving. It has an affinity towards the metal, iron. So it goes into the core. So if the Earth's core basically formed very late, that means, let's say it formed 500 million years after formation of the solar system, then your 182 hafnium would have decayed by then, right? It has decayed in the first 50 million years. And so the radiogenic 182 tungsten that you produce because of 182 hafnium decay is all in the Earth's core. And so you would not really find any excess in 182 tungsten relative to a standard, and the standard typically is taken as this Quadratic Meteorite because nothing really happened to them. But what the real data actually shows is that you have an excess in 182 tungsten in mantle rocks of the Earth. See, we don't have samples of the Earth's core, right? So we have samples of the Earth's mantle, and there we find an excess in 182 tungsten, which means that the Earth's mantle and core were not in talking terms, even when 182 hafnium was alive. Hafnium is a silicate-loving material, so it's in the mantle. It decays, but if the tungsten is there, that means it never went into the Earth's core. It did not go into the Earth's core because the core had already solidified by then. So the presence of these excesses in 182 tungsten in the Earth's mantle rocks essentially gives us some time constraints and when the Earth's core had formed and crystallized. And because the Earth's core formation is synonymous, it happened by the same process as this moon-forming giant impact, we can now link this information to the timing of the formation of the moon. Of course, whether it's 30 million years or 45 million years, some people say it could be even longer. Those are the complexities, right? Because we also need to bring in some models of core formation, because it's not very simple. The core, it's not that you had all liquid and the core just went plop. It did not happen like that. The magma ocean was only 600 kilometers thick or so. So the process of transferring metal to the center of a planet is a long drawn process. It's not instantaneous. So while I said that it's about 30 million years, you make some assumptions as to what is your core formation model. However, these are supported by these hafnium tungsten isotope data.
Oh, that's excellent. Thank you so much.
Bhattacharya, go next.
Very nice talk indeed. Now, I had a question about the slide you showed, the Wang et al. Result on the potassium correlation with mass, radius, surface gravity, and escape velocity. If we could go to that slide, that's slight confusion.
Yeah, so this is taken from a recent paper by Tian et al.
So what is it in the vertical axis over here?
So the vertical axis is again your potassium isotopic composition. So this is your delta 41 potassium, which is what I presented here on the left on the x-axis. Okay, so this is the isotopic composition.
These quantities, they are all related to each other. Escape velocity depends on surface gravity. And surface
absolutely. So
let us take one of these as
any one of these, yes.
Let's take surface gravity as indicator.
Perfect.
So for higher surface gravity, you have lower concentration of volatile.
So this is, I wouldn't say concentration of volatile. I would say this is a ratio of 41 potassium over 39 potassium. Okay. So that means.
How does one interpret this?
Yes. I'll try to explain that. So if you have a bigger planet, and let's say you had some collision, or let's say some impact radiating, or whatever it is, a process that can induce volatilization. If you during volatilization, because if you look at the 0-point energies of 39 potassium and 41 potassium, the lighter isotopes, the ones with lower masses, typically have a higher 0-point energy. And so when you supply some energy to the system, let's say you have a solid and you supply some energy to the system, and let's say things vaporize. And let's say if you have liquid water and it vaporizes, the lighter isotopes typically take part in the reaction much faster. So they go to the vapor phase. So in case of this volatilization kind of a scenario, you would expect that the vapor phase will actually have more of the lighter isotopes. And so the residual solid, right, will actually be enriched in the heavier isotope, which means that this delta value is actually going to increase. So you can see that the higher values for 4 Vesta means that it has lost more of its lighter isotopes, which is equivalent to saying that more potassium actually volatilized, compared to, let's say, a body like the Earth, where there is less volatile loss of potassium and hence less volatile loss of the lighter isotopes, and hence a lower value of this delta 41, which is nothing but the 41 by 39 ratio.
Right. So the vertical axis is a measure of depletion, basically.
It is an isotopic measurement, yes, which in turn.
Then I understand that higher surface gravity, you have lower depletion.
That's right.
Now, you also said that this potassium concentration is affected by aqueous activity.
That's right, yes.
So in that case, should one expect such a tight correlation, or since the aqueous activity on the surface of these different planets and planetary bodies are probably different, right?
Yes, that's a very good question, actually. So now, when we look at samples of the Earth, even though this is shown here by a single data point, if I go a step back, this gray axis out here, this gray vertical bar, is possibly an average over 100 measurements of different kinds of rocks. And of course, we know that low temperature alteration can, because modern seawater is a little heavy. Okay, so when you break down minerals by aqueous activity and clay formation happens, there is fractionation of isotopes. But we pick samples that have not been affected by aqueous activity when we are trying to estimate the composition of a bulk planetary body like the Earth, because we have so many samples, right? So when we look at this kind of a plot, and the single point for the Earth is based on measurements of terrestrial samples that have not been affected by aqueous activity. So when you see a trend of this kind for a bulk planetary context, these are unlikely to have been affected by aqueous alteration. I mentioned aqueous alteration when I look at these individual scale ordinary chondrites. So if you let's pick one of these bars out here. OC means ordinary chondrites, and these are samples that were tracked when they fell, right? And you can see that within these similar class of meteorites, there's a large range in potassium isotopic compositions. And some of these, there are other proxies by which we can, kind of figure out how much of this object has been aqueous altered, how much of this object has seen metamorphism. So there are classifications. And in some cases, although there is no clear correlation with other proxies of aqueous alteration, we are still unable to rule it out completely. So that means each of these ordinary chondrites essentially represent a different parent body, which had a very similar composition. But because and these are one sample from each of those parent bodies, right? So while, it would be nice if they all had a very tight, low variability kind of a composition, but the fact that you actually have some kind of a variability, there is some correlation with proxies of aqueous alteration, but not very distinct. So volatile loss is indeed one of the possibilities as to why you have this spread, but parent body alteration cannot completely be ruled out. Now, you also have to realize that, because volatile loss will cause depletion of the lighter isotopes and make this value higher. When you look at these ordinary chondrites, you see that the values are actually lower. So, one cannot really, invoke a simplistic picture of volatile loss in some of these chondrite parent bodies. There could be multiple processes that are actually affecting this isotope system. And so only time will tell. So, there are more detailed studies that need to come in, focusing on maybe one set of meteorites and basically, then inferring that for this one parent body, it was aqueous alteration. For the other parent body, it could have just been volatile loss.
Thanks very much.
Sure.
Thank you. That makes sense. Anybody else? I think we've a lot of our audience is also evaporated.
Volatile loss.
Volatile loss. We are losing them very fast. I don't know what kind of aqueous activity that can be. Okay, thank you very much, Ramananda, for this great talk. And then we can't applaud on Zoom very well, but wonderful. Kandu, did you have to say anything?
No, thanks a lot. I mean, for this, nothing more to add.
Extremely thought-provoking, and a lot of people, I think, and the people who are genuinely interested have asked a lot of questions.
Sure.
We hope we continue this dialogue, and very soon we'll see you in person at some point.
Absolutely, and thank you again for the opportunity. And I look forward to more potential discussions in the future.
Great, thanks, Ramananda. Bye.
Great.
Thank you. Thanks a lot.